Our question today is, what is impulse? Just like a force can cause a change in velocity, an impulse is going to cause a change in momentum. And so we define impulse as a change in momentum. Now, it depends not only on force, but on the length of the time that force is applied as well. We're going to look a little bit later as to how the length of time can affect the amount of impulse and the amount of force acting on the object. Now, the momentum will change if the mass changes, the velocity changes, or both. You might say, well, when would the mass change for an object? And that happens quite often. Whenever you're driving in your car, as you drive, your car is using up the gasoline, and some of the mass is coming out the exhaust after the combustion takes place. So as you drive your car, the mass is changing, and therefore its momentum is changing, even though you may be moving at the same velocity. Most times, though, we think of the momentum changing as if we increase or decrease the velocity, if we speed up or slow down. And finally, the momentum can change, of course, if both of those take place, both the mass and the velocity changes, as usually is the case as we're driving our car. Now, when you push with the same force for twice the amount of time, you impart twice the impulse and produce twice the change in momentum. So if I push the car, as you can see in the diagram, the picture below, what is happening is the car is speeding up. If I push for twice as long, the car is sped up to twice the velocity, and therefore the momentum is increased twice the amount. So if I push that car for twice the amount of time, I will have twice the impulse. Now, to calculate the impulse, I have the formula down below here, and what I'd like you to write in your notes is simply write down this circle equation. That quantity of force times the time, if we multiply the force and the time, we are going to get the impulse, which is also known as the change in momentum. So to get the impulse, we can either multiply the force times the time, or we can subtract the momentum in the beginning from the momentum at the end. And so we see here that the impulse is affected by both the force and the time, and different forces exerted over different time intervals can produce the same amount of impulse. Either we can apply a large force over a small amount of time, or if we apply a small force over a large amount of time, we can get the same impulse. For example, pushing that car. If you push the car with a small amount of force, it'll take a large amount of time in order to get it up to a large momentum. Or we can give it a large force over a small amount of time and get it to that same velocity, that same amount of momentum. This kind of brings us to this question, why is it necessary to follow through when hitting a golf ball or a baseball? You never want to, when you're swinging your golf club, stop the motion without following through. Same as a baseball. Your coach will tell you as you swing the bat, you want to swing all the way through and not stop as soon as the bat connects with the ball. So I want you to pause the video here, and I want you to write down your thoughts using impulse, why it's necessary to follow through when hitting a golf ball or baseball. After you've written your response, you can unpause the video and see how well you did. Welcome back. So our question was, why is it necessary to follow through when hitting a golf ball or a baseball? And our answer is, when a golfer or a baseball player follows through, they make the time interval as long as possible. We want to have a large amount of time. This will cause the largest impulse or increase in momentum. If you apply that force, the longer you apply the force, the faster it keeps getting. And so if you apply it for that long amount of time by following through, it'll make it as fast as possible. Now, let's say you were in a car that just came out of control and you couldn't control where the car was going, and you had to choose between hitting a haystack to stop it or hitting a concrete wall. Well, of course you choose the haystack. You already know that. Well, physics helps us to understand why hitting the softer object, like the haystack, is entirely different than hitting the harder surface, which is the concrete wall. We're going to go through some calculations in order to see why this is the case. So let's look first at hitting the haystack. So when we hit the haystack, this change in momentum occurs over a long amount of time, and therefore it'll make the force rather small. So let's say we have some data. The mass of the car is 1,400 kilograms. The initial velocity of the car is 25 meters per second, which is about 50 miles per hour. And of course, the final velocity is 0. We're eventually going to come to a stop. When we hit the haystack, we're going to come to a stop over a long amount of time. So perhaps 2.3 seconds in order to come to that stop. In order to solve here, what we're going to do first is we're going to calculate the initial momentum of the car. And so we have in our data, we said that the car has a mass of 1,400 kilograms. And we said that the initial velocity was 25 meters per second. We're going to solve for that momentum. So go ahead and pause the video and solve for that momentum. And when you're ready, unpause and see how well you did. Okay, welcome back. We are going to solve for that momentum. In order to do so, we're going to multiply the mass times the velocity. Our mass was 1,400 kilograms. Our velocity is 25 meters per second. And so we get a momentum of 35,000. And the units would be a kilogram times meter per second. Next thing we have to do is we have to solve for the final momentum. Well, the mass of the car is still 1,400 kilograms, but the car comes to a stop, so the final velocity is 0. What I would like you to do is, again, pause the video, solve for the momentum, and once you're done, unpause the video and see how well you did. Welcome back. To solve for the momentum, again, it is mass times velocity. Mass is 1,400 kilograms, and the velocity is 0. And we get a momentum of 0 kilograms times meters per second. The next step is we're going to find the impulse, which is the change in momentum. We're given that the first momentum was 35,000 kilograms times meters per second. That was the first momentum we calculated in this problem. And the second momentum we calculated was 0 kilograms times meters per second. We're going to solve for that impulse. So what I'd like you to do is pause the video, solve for that impulse, which is the change in momentum. And when you're done, unpause the video and see how well you did. Welcome back. Make sure you write these in the correct order. It is 0 minus. The second is 0. So 0 minus 35,000 kilograms times meters per second, which gives us an answer of negative 35,000 kilograms times meters per second. Now the final step here is to solve for the amount of force that acted on the car and the people inside the car. In order to do that, we just saw that the impulse is negative 35,000 kilograms times meters per second. And we were told in the problem that the time is 2.3 seconds. We're going to solve for that force. So what I'd like you to do is I want you to pause the video, solve for the amount of force acting on the people inside the car, and when you're done, unpause the video and see how well you did. Welcome back. We are going to solve for that force by dividing the impulse and the time. Our impulse is negative 35,000 kilograms times meters per second, and our time is 2.3 seconds. And so we get an answer here of a force of negative 15,217 newtons. So when the car hits the haystack, the force is negative because it slows it down. And it's a negative 15,217 newtons. Now what we want to do next is we're actually going to solve for what would happen if we were to hit that concrete wall instead. And the only difference here, mass of the car is the same, velocity is still the same, final velocity is the same. The only difference here is the time is shorter. So we have a shorter amount of time. So I want you to go through here and solve. And once you're done solving, unpause. It's the same types of problems, but when you're done, unpause and see how well you did. Okay, welcome back. So in this problem here, we have the mass of 14,000 kilograms. The initial velocity, or first velocity, is 25, and we're solving for the momentum. We're going to take the mass times the velocity. And what you should notice here that the momentum is still the same. Whether you hit that haystack or that concrete wall, you start with the same momentum. What you should also notice here is that the final momentum is also going to be the same, because we end with the same zero velocity. And therefore, your change in momentum or impulse will also be the same value. Which is negative 35,000 kilograms times meters per second. So whether we hit the haystack or the concrete wall, our impulse will be negative 35,000 for both situations. But here's where the difference occurs. Our time is now 0.45 seconds. To solve for the force, we take the impulse and divide by the time. And we get a force in this case of negative 77,778 newtons, which is a lot larger than when we hit the haystack. So how does the force from the haystack collision compare with the force from the concrete wall collision? Well, the force from the haystack is much less than the force from the concrete wall. 15,000 from the haystack versus 77,000 from the concrete wall. And so to keep the force small, we make the time larger. So we see that no matter what, we're going to have the same impulse. So either you have a large time and a small force, or you have a small time and a large force. So you have to determine what do you want to be the smaller value, the force or the time.